Welcome to the video on Computer-Aided Drug Delivery System, or CADDS. I am Dr. Krishna Yadav, and this is Unit Number 1, Part 5.
This video focuses on sensitivity analysis, a crucial topic in pharmaceutical research and development. Sensitivity analysis can be intuitively understood using a steering analogy, where high sensitivity means a small input causes a drastic change in direction, and low sensitivity means a large input causes only a mild change. Sensitivity analysis is a quantitative technique that determines how changes in input variables affect model outputs. It is essential for identifying critical formulation and process variables, impacting product performance, safety, and efficacy. Sensitivity analysis systematically evaluates how variation in model inputs affects variation in model outputs. Mathematically, it addresses the key question: which variable matters the most? In pharmaceutical sciences, sensitivity analysis is important for identifying critical variables, supporting quality by design, assessing robustness, reducing development costs, and guiding risk assessment for improved model reliability. Consider a sustained-release tablet influenced by polymer concentration, compression force, and binder level. If a small change in polymer concentration leads to a drastic change in drug release, it is the critical variable, demonstrating high sensitivity. The sensitivity index, S_I, is the mathematical representation of the partial derivative of the output Y with respect to the input X_I. A large index means high sensitivity, and a small index means low sensitivity. Normalization is crucial for direct comparison of variables, as it removes units and scaling effects. This enables a direct mathematical ranking of variable importance, allowing for the comparison of disparate variables. The two main types are local and global sensitivity analysis. Local analysis uses derivatives for small changes around a fixed point, suitable for deterministic models. Global analysis evaluates the entire input range, considering interactions, and is more robust. Local analysis is best for deterministic models, like PK parameter estimation, but may miss nonlinear effects. Global analysis uses methods like Monte Carlo simulation and is applied in PBPK modeling, but it is computationally intensive. Sensitivity can be graphically represented using a response surface. A steep slope indicates high sensitivity, while a flat slope indicates low sensitivity. For example, a steep gradient for sorbitol suggests it is the more sensitive variable. The 3D surface plot illustrates the response surface. The steep slope due to sorbitol reveals high sensitivity and identifies it as the critical variable. The flat slope due to agitation shows low sensitivity and system robustness to this parameter. A parameter sensitivity graph shows that as variation amplitude increases, the internal friction angle and unit weight show the highest sensitivity. Cohesion and relative water content, on the other hand, show the lowest sensitivity. Tornado diagrams visually rank variable importance. In the pharmacoeconomic model shown, the utility of PFS state has the greatest impact on ICER, while the annual discount rate has the least impact, guiding analytical focus. The diagnostic dashboard provides a unified view, combining the parameter variation chart and the tornado diagram. The key takeaway is the identification and ranking of influential parameters for robust decision-making. In application case 1, formulation optimization, the dissolution Y depends on polymer X1 and lubricant X2. The analysis shows polymer has a strong positive and quadratic effect, while lubricant has a weak negative effect. For application case 2, pharmacokinetics, the one-compartment model is highly sensitive to clearance. Clinical implication is that patients with impaired clearance need individualized dose adjustments to maintain therapeutic concentrations and avoid toxicity. Sensitivity analysis plays a crucial role in quality by design. It identifies critical material attributes and critical process parameters. High sensitivity variables require tight control, while low sensitivity variables permit broader acceptable ranges. Sensitivity analysis and optimization differ in their goals. Optimization finds the best point, whereas sensitivity analysis checks how stable that point is. Both are essential for reliable outcomes. This conceptual plot further illustrates the difference. Optimization finds the maximal point. Sensitivity analysis evaluates the robustness of that optimum, showing that the system is stable near the optimal polymer concentration. In regulatory science, sensitivity analysis meets expectations for risk-based justification and robust design. It supports process validation, stability justification, and scale-up decisions. From a practical standpoint, high-sensitivity variables are critical parameters requiring strict control. Low-sensitivity variables can have wider acceptance criteria, reducing manufacturing constraints and risk. Advantages include identifying critical factors and defining the design space. Limitations include dependence on model accuracy and the potential for high computational intensity in global analyses. To summarize, sensitivity analysis quantifies input-output relationships and identifies critical variables. It bridges theoretical modeling and practical pharmaceutical development, which is essential for quality by design and regulatory compliance.
Thank you for watching this video on sensitivity analysis. We hope this information is useful for your work in pharmaceutical research and development. Please like, share, and subscribe.